So as the title indicates the talk will be on Bieberbach theorem for compact plane waves. So I don't know how to make this full screen. Okay. What is Bieberbach theorem? First, in the Riemannian setting, so a compact flat Riemannian manifold is a quotient of Euclidean space by a discrete subgroup of the isometry group, the Euclidean group, which acts properly, freely, and co-compactly on Rn. Okay, and Bieberbach theorem states that for any here proper action means that for any compact subset of Rn, we only have a compact set of elements gamma such that when we apply gamma to K, gamma K intersect K only for a compact compact set of elements gamma. Here, when gamma is discrete, the action is automatically proper. So gamma will be only a discrete. Gamma is in fact a discrete subgroup with acting freely and co-compactly on Rn. Bieberbach theorem says that for any discrete subgroup of the isometry group of Rn, isometry group for the Euclidean flat metric on Rn. For any discrete subgroup gamma of the Euclidean group, which is co-compact, the intersection of gamma with the translation part, Rn, has finite index in gamma. So this means that gamma contains n linearly independent translations. So this is the algebraic statement. Geometrically, this means that, or topologically, this means that the fundamental group of a compact flat Riemannian manifold is contained, up to finite index, is contained in the translation part of the isometry group in Rn. So a compact flat Riemannian manifold is finitely covered by a torus. The Lorentzian Lorentzian Bieberbach theorem. So the Lorentzian flat case. The Lorentzian flat case is much more complicated. Here, first, in the Riemannian case, the fact that a compact flat Riemannian manifold is a quotient like this is straightforward, because here, so here in the Riemannian setting we have J, we have the isometry group which acts transitively on Rn with isotropy compact here. A flat compact Riemannian manifold is complete, so it is directly a quotient like this. But in the Lorentzian case, this is not obvious, and this is a theorem by Carrière that says that a compact flat Lorentzian manifold is the quotient of Minkowski space. Minkowski space is Rn plus 1. So Minkowski space of dimension n plus 1 is Rn plus 1 equipped with, should have written the metric with the Lorentzian flat metric. The isometry group for this space is this one. We call it the Lorentz group. or the Poincaré group, sorry. The Lorentz group is the isotropy. Carrière says that a compact flat Lorentzian manifold is a quotient by a discrete subgroup gamma of the isometry group that acts properly, freely, and co-compactly. Here, contrary to the Riemannian case, the proper condition here is a true condition. It's not easy to check, and not any discrete subgroup of the isometry group acts properly. So here it's a true condition on gamma. The theorem, the analog theorem to Bieberbach, which interests us here, is standardness, and this is proved by Goldman-Fried-Kamishima. Here it says that up to finite index, gamma is a co-compact lattice in a solvable connected Lie subgroup L of the isometry group that acts simply transitively. So in the Riemannian case, L was the translation part of the isometry group. Any gamma is, in the Riemannian case, flat case, any gamma is up to finite index contained in Rn. Here, they prove that gamma is a co-compact lattice in some Lie subgroup L, which is solvable, connected, and acts simply transitively. Simply means freely. So in this case, since L, this group L acts freely transitively on the Minkowski space, we pull back the metric on it. We get M as a quotient of a left invariant metric on L by gamma. Gamma is the fundamental group of M. Okay. So in fact, we have a more general statement. They prove a more general statement in a paper of Goldman and Fried. They prove that any subgroup, any discrete subgroup gamma of the affine group, which is solvable, so they assume it to be solvable, acting properly co-compactly on Rn. For any such group, gamma is up to finite index, a co-compact lattice in some solvable Lie subgroup of the affine group, acting simply transitively on Rn. So here they assume that gamma is solvable. There is a conjecture by Oslander that says that any such gamma will be in fact solvable, but it's not proved. And Goldman-Kamishima proved this conjecture in the case of the Poincaré group, the subgroup of the affine group preserving Lorentzian flat metric. So they prove that the fundamental group of any compact flat Lorentzian manifold is solvable. And with this general statement, we get this statement I gave just before, that gamma is a co-compact lattice in some solvable Lie subgroup of the isometry group. Okay, so here the difference between the Riemannian and the Lorentzian case. First, in the Riemannian case, we have a compact isotropy. Okay, so any discrete subgroup will have proper action. And here we have non-compact isotropy. So here Here, the properness is a difficult condition on gamma. The second thing is that this group is the algebraic structure of the Lorentzian group ON1 is much more complicated than the Euclidean one. In ON, all elements act in all elements are diagonalizable, are semi-simple on Rn. Here we have unipotent elements, semi-simple elements, and mixed. So the algebraic structure here is much more complicated. And in fact, the difficult thing here is that to prove the existence of this group, this Lie group L. The fact that it acts simply transitively will follow directly from this fact, classical fact. So, if we have a Lie group, a connected Lie group with a co-compact lattice, if it acts properly co-compactly on a contractible manifold, then it acts transitively. We'll use this fact for our manifolds. Okay, the general context for this standardness is the compact quotients of homogeneous spaces. So if X is a homogeneous space of a Lie group J, so if we have a Lie group J acting transitively faithfully on X, X will identify as a quotient of the Lie group J by a closed subgroup of J, which is the subgroup fixing some base point in X, the isotropy. So we consider a homogeneous space of like this of a Lie group J. A compact quotient of X is a quotient of X under the left action of a subgroup gamma of J, acting properly, freely and co-compactly on X. So X mod the left quotient of X by gamma will give a compact manifold, and X will be a covering of X mod gamma. The interesting situation is when J preserves some geometric structure on X. In this case, the quotient, in this case, the quotient of X will carry a geometric structure isomorphic to that of X. So here, the flat Riemannian and the flat Lorentzian cases were examples of this situation with exactly those groups. Here for the Riemannian case, and here for the Lorentzian case. Yeah, I already commented on this. Here it's the comment on the isotropy. When the isotropy is compact, it's exactly the case where J preserves a Riemannian metric on X. And here any discrete subgroup acts properly. And in fact, any discrete subgroup acting properly will be a co-compact lattice in J. Standardness question. So we consider again X a homogeneous space of a Lie group J, and M a quotient of X by a discrete subgroup acting properly co-compactly on X. The standardness question is the following: is gamma a co-compact lattice of some Lie subgroup A, L of J. The answer was yes in the case of Riemannian flat and Lorentzian flat manifold, compact manifold. In the case where there is some a connected Lie subgroup L of J which acts properly co-compactly on X, then any uniform lattice in L will act also properly co-compactly. So here it's the converse, which also holds. And in general, finding L is easier than finding gamma. That's why this question in general is interesting. So we call a compact quotient standard if we have such a Lie group, if gamma can be embedded as a co-compact lattice in a connected subgroup of J, which acts properly co-compactly on X. And this L, this connected Lie group, will be called a synthetic hull for gamma. We have some standardness results. So maybe the most the easiest situation is this one. We consider a translation structure. So here J is simply Rn. I is some subspace in Rn, Rk, quotient space. Here a subgroup gamma of J acting properly co-compactly on the quotient J mod I is just a discrete subgroup of J which does not meet with empty intersection with I, and which is of rank n minus k, maximal, such that the quotient of J mod I mod gamma is compact. Here, a synthetic hull of gamma is simply the linear subspace generated by gamma. Here, gamma is made of translations, and the synthetic hull is the Lie group of translations that contains gamma, generated by gamma. So a generalization of this situation Rn is when J is a simply connected nilpotent group. Here, any gamma has a synthetic hull, which is called Malchev closure, which coincides with the Zariski closure of gamma in J. A simply connected nilpotent group is an algebraic group, and the synthetic hull here is just the Zariski closure of gamma. In the solvable case, there is no Malchev closure. And for example, if you consider the universal cover of the Euclidean group dimension 2, so how to see this group? This is simply the subgroup of the Euclidean group of dimension 3, which preserves. You can see this inside the Euclidean group of dimension 3, which preserves a time-like vector, or which preserves some vector. Here, yes, solvable but not nilpotent. Yeah, in the general solvable case, there is no Malchev closure. So here, the group is R2, we take the R2 inside R3, two translations, and R, you see it inside this group. It's you take a one parameter group here, which preserves which preserves this plane. So and acts with a rotation on R2. Okay, so here R, if you see R acting on R3, it acts as a rotation on R2 together with a translation in the Riemannian direction. You consider gamma. So here inside this group, you have this one Z times R2. Z is the time one the time one of the rotation. So the element of the one parameter group of the rotation which acts trivially on R2. Here we have so we have a discrete subgroup here Z in R, which acts trivially on R2. So you have Z times R2 inside the universal cover of the Euclidean group. Inside this, you consider this discrete subgroup. Z is the first factor, and the second is some discrete subgroup, cyclic subgroup in R2. This gamma does not have a symplectic hole in J, because you take any line containing this Z, this second factor Z. Any one parameter group containing the first factor will rotate this line. So we cannot find something of dimension 2 that contains gamma inside J. Okay, so the solvable case is difficult with respect to this synthetical construction. Okay, so this was the solvable case. In the semi-simple case, when J is semi-simple, here in this setting, the geometric setting we have here is the manifolds, compact manifolds with negative curvature. I will not comment on this much, but in dimension 3, there are no standard examples constructed by Goldman. So this corresponds to the J here corresponds to the isometry group of anti-de Sitter space. The mixed type, which is the closest case to our situation, is mixed type means that we have in J we have both a semi-simple part and the solvable part. The Riemannian case here, the cases of Riemannian flat and Lorentzian flat are inside this case. So here and here we have these existence theorems by Bieberbach and Goldman-Kamishima Fried for the synthetic holes. Okay, let me say that in the Riemannian flat case, so Bieberbach says that any gamma is contained up to finite index in Rn. So Rn, the translation part here, is a synthetic hole for any gamma. In the Lorentzian case, we have much more examples of synthetic holes. Not only so, for example, in dimension 3, Lorentzian flat case in dimension 3, you consider the Lorentzian flat metric on R3 represented this way. The isometry group is this one. So here, as if you take R3, you take any R3. R3 acts freely transitively on R3 by translations. So any subgroup discrete, any lattice in R3 will act also properly co-compactly and with synthetic rule R3. Now other examples are given by the followings. So the second one is Sol. Here okay. Here you consider inside this group, you consider the subgroup which preserves a space-like vector, for example, which preserves dx, okay, which is space-like. If it preserves dx, then it preserves the orthogonal of dx. The orthogonal of dx is a Lorentzian plane, is du dv, generated by u and v. It's a Lorentzian flat plane. So the subgroup of this which preserves this space-like vector dx is R times R3. Well, it contains the R3, all the translations, and a one-parameter group inside this group, which is this matrix here. This big matrix are okay. One this matrix is represents the subgroup of the O12 that preserves the dx, and then inside this group we take this three-dimensional connected subgroup, in which we take we take the two translations in the x and u directions, and we take a third one-parameter group, which is transversal to R3 and generated by the composition of this matrix and translation with translation in V. Okay, here we have the one-parameter group here R is represented by T here. This group is called Sol, and it acts simply transitively on R3. Okay, by preserving the space-like vector, and any lattice co-compact lattice here has Sol as a synthetic rule. For this example, another example is a synthetic rule which preserves a null vector. Here, so for example, here dv is a null vector. If you look at the subgroup of the isometry group which preserves dv, we have the full group of translations, R3, and together with this matrix, one-parameter group of unipotent matrices, this is an element in this matrix. This big matrix is an element in O12. And we, inside this group, we take a connected group of dimension 3, in which we take the, sorry, yeah. It's not this, not the right presentation here, sorry. T here should be in the first component. Okay, so here we take two translations, X and U, R2 here, and a third one-parameter group, which is generated by this matrix, unipotent this one-parameter group of unipotent matrices, together with the translation in the v coordinate. I made a mistake here. In order for this to be in order for this to be a one parameter group, the translation vector I choose here has to be in the center. It has to be fixed by this one parameter group. So it is the eigenvector, this eigenvector. So this group is isomorphic to Heisenberg group of dimension 3. It acts transitively because we have all the directions. And again, any lattice here will have has H3 as a synthetic hole. Here, of course, when we consider R3, the quotient of R3 by some lattice or sol H3, these manifolds are all, we get compact flat Lorentzian manifolds, which are all locally isomorphic, okay? But globally they're not the same. For instance, here, when we, with this choice of synthetic hole R3, we have all the translations here are preserved by any subgroup gamma. So they will be well defined on the quotient. So on the quotient, we will have 3 parallel vector fields. Here, Sol preserves one vector, which is the eigenvector here, which is Sol preserves, here we will have a well-defined parallel space-like parallel line on the quotient. And here we have a well-defined null parallel vector field on the quotient. Okay. So our situation is the following. So the problem for us will we'll consider homogeneous spaces, and we will ask standardized questions for these homogeneous spaces. These homogeneous spaces are the following. So we define J to be this group. So it's I have here a Heisenberg group of dimension 2n plus 1, and extension of this group by R times K. Here, K is a closed subgroup of On, which acts on Heis in some way. So I will recall the definition of Heis and the Heisenberg group and all this. The question is the same as in for Bieberbach and the Lorentzian case. It's about the standardness of compact quotients. So here, the Heisenberg group of dimension 2n plus 1 is the subgroup of the affine group, which is represented in this way. So we have the full group of translations, Rn plus 1, okay? And we have this subgroup inside the GLN of Rn plus 1. Which contains these unipotent matrices, okay? So this abelian subgroup of unipotent matrices, we call it A plus. In the translation part, we have the eigenvector of these matrices, which is the first vector here, is the center of Heis. It is one-dimensional. And the remaining part of the translation group here, we call it A minus. This is the usual representation of the Heisenberg group inside this group, inside the affine group of Rn plus 1. And we call this the usual action of the Heisenberg group on Rn plus 1. So here, Heis is this group, and K is a subgroup ON, which acts on Heisenberg group trivially on the center and by standard action of ON on A plus and A minus. A plus is a space which is isomorphic Rn. A minus also is Rn. We act, the orthogonal group acts on it by standard action. The isotropy here is K semi-direct product with A plus, and the homogeneous space is J mod I. So some vocabulary here. On Rn plus 1 endowed with this light-like quadratic form, this one. So on Rn plus 1, I consider coordinates V, x1, xn, with the light-like quadratic form, which is degenerate. Light-like means that it is, okay. This is a quadratic form on Rn plus 1, which is Riemannian, but it's degenerate, and it has one-dimensional kernel, which is the direction of V. The subgroup, the group of affine isometries of this quadratic form, which preserves V, this light-like direction, is exactly this group. ON semi-direct with a Heisenberg group of dimension to n plus 1, which is represented in this way. So here, if you put identity instead of A, you have the Heisenberg group of dimension to n plus 1, which acts on Rn plus 1 by preserving the V direction. So it preserves a vector, which is light-like. Light-like means that its norm with respect to this quadratic form is 0. And it preserves this this vector. And on the quotient space, Rn plus 1, quotient of Rn plus 1 by this direction, it preserves on the quotient space, we have this well-defined Riemannian scalar product. It preserves this scalar product. And this is true also if we put here an orthogonal matrix instead of the identity. So this is in fact the maximal subgroup of the affine group, which preserves this quadratic form and this vector V. And we call it the affine unimodular light-like group. Okay, and any manifold in which is modeled on this structure, Lu, will said to have an affine unimodular light-like geometry. So here in my group here, K semi-direct Heis is in fact a subgroup of this affine light-like unimodular group of this Lu. So when we consider this homogeneous space, which J invariant objects do we have on X? We have a codimension 1 foliation defined by the action of this subgroup. Here, K semi-direct Heis to n plus 1 is a normal subgroup of J. So when we act by H, we have a well-defined, we have a foliation on J mod I, which is preserved by the action on J. Okay, the leaf through, I call this group H. The leaf through a point Ji is simply this subset inside J. And when I act on it by an element G prime of J, if I act on a leaf, it maps this leaf on the leaf through the point G prime J. So I have a foliation. And by definition, the leaves of this foliation are modeled on the affine unimodular light-like geometry. because this subgroup here is a subgroup of LU. So I have on each leaf, I have a well-defined vector field. Okay, here this vector V, in fact, it is generated by the action of the center of Heisenberg, the eigenvector of this matrices, which is exactly the center of the Heisenberg group. So when I act by the center of Heisenberg group, I have a well-defined vector field, which is tangent to this foliation. I have a degenerate Riemannian metric along the leaves, and the flow of R, here, this one, induces an isometry between the leaves, isometry with respect to this finely modulate-like structure. Well, I'm running out of time. Okay, a question now is, so I have this homogeneous space. On this homogeneous space, I have a well-defined foliation, which has a light-like unimodular structure. The question is when do we have a well-defined, when does the J action, so sorry, J acts on the left on X. The question is when does J preserve a Lorentzian metric on the quotient? Maybe I will stop here for this first part and I continue later.